myself Shwetnisha. So today we are going to dive into another topic, which is going to be linear algebra. Linear algebra, we are discussing 2022 exam questions from your exam 2022, and before we jump into the mathematical intricacies, I want to take a moment to talk about something which is equally important. As many of you know that the right guidance and preparations can make all the difference. And that's why I want to make a special shout out to Plutus IS based in Karol Bagh, Delhi. Their dedication to helping out UPSC aspirants to achieve their dreams is really commendable, and you can definitely check out the link in the description below. Even if you are not preparing for the UPSC and you're preparing for some other exam, other government exam, you can definitely go through their websites, and you can talk to their counselors, because they provide the best counseling also. So coming back to the main focus, the year 2022 brought forth some really good problems, solving opportunities that we are going to do together for the linear algebra. So without wasting any time, let's get started. So this is, we are solving UPSC Mathematics Optional questions from 2022. So this was the basic format of your exam. As you can see from the linear algebra section, I have highlighted here. It is only the part A of your paper, and question number 1, which is a mandatory question to attempt all the parts. So first two questions are from linear algebra, and then second, first, third, there were 2 parts for it from linear algebra, and fourth A. So we are going to discuss each and every question one by one. Let's start. First question. First question is, prove that any set of n linearly independent vectors in a vector space V of dimension n constitute a basis of V. So let's try to understand what the question says. Question says that, it has given you something and you want to prove something, right? So it's better that whatever given in the question, you write it first, right? And then you will understand that, okay, these are the things that we need to use, and this is something that we want to prove, right? So what is given? If they're talking about a vector space, so let S is equals to V1, V2, and so on till Vn. Be a subset of V such that S is linearly independent set. So that's what the question says. Prove that any set of n linearly independent vectors. So here I have taken a set which consists of n vectors, and I have taken them to be linearly independent. It is also given that the vector space is of n dimension. Also, dimension of V is n. We want to prove that S is a basis. To prove this, S is a basis of it. Okay. If you look at the definition, what is the definition of being a basis? There are 2 points that needs to be satisfied, and those 2 points are, first, S needs to be a linearly independent set. So there are 2 points that we want to prove. S is linearly independent set, and number 2 is that linear span of S is going to be V. These are the 2 things that we want to prove. But if you look closely, this is something that is already given to us. So it is already given that S is linearly independent, right? That means I just have to prove a second point, which is being the linear span. If I can prove linear span of S is V, that means I'm good too, right? So in order to prove this, we will prove that linear span of S, that is going to be represented as L of S is equals to V, the whole vector space. So there are two sets. I want to prove two sets to be equal. How to do that? We'll prove one is a subset of other. Now, S is a subset of V that we have taken in the very beginning, right? Next. What does it mean? See, S is a subset of V, but V is a vector space. If V is a vector space, that means if I take two vectors from a vector space and if I talk about their linear combination, then that will be also in the vector space, right? So here I have taken S as a subset. So the linear span of S will also be subset of V. The reason being because V is a vector space, right? So one part of the equality is already proved. The L of S is a subset. Now we'll talk about the other way around. V, how can I say that V is also a subset of L of S? To prove this, how we can prove? I'll take an arbitrary element. Let V belongs to V. Be an arbitrary element. Be an arbitrary element. So, and what we want to prove? We want to prove that this V belongs to L of S. That means I want to prove that this small v can be written as a linear combination of the vectors in capital S. So to do that, consider A, which is V1, V2, Vn, and V. So basically, I have taken S with a union of set containing this element small v. So I have taken the union as this, and this is capital A. Then, can I say that capital A is linearly dependent set? A is linearly dependent set. It is very obvious. Why? Because the vector space is of dimension n. Vector space is of dimension n, and I have taken n plus 1 element. So definitely this will be the linearly dependent set. Because dimension of V is n and number of elements in A is what? N plus 1. Therefore, if they are linearly dependent, let's apply definition of being linearly dependent. Therefore, there exists alpha 1, alpha 2, and so on. Alpha n minus 1, alpha n, alpha, not all zeros, such that alpha 1 v1 plus alpha 2 v2 plus and so on. Alpha n minus 1 v n minus 1 plus alpha n vn plus alpha v is equals to 0. I have already written that all of them are not 0. This is from the definition of linearly dependent. Now, if I talk about in particularly this alpha can be 0, can be non-zero. Let's discuss both of the cases. Let alpha is equals to 0, which implies alpha 1 v1 plus alpha 2 v2 and so on, alpha n vn. That becomes 0. But they are v1, v2, vn. They are what? They are linearly independent set. So it means alpha 1, alpha 2, everything is 0 because S is linearly independent set, but it's a contradiction because I have taken alpha to be 0, then all the other elements are also 0. which means all scalars are 0, but that contradicts the definition of being linearly independent set, which says they are all non-zero, right? Which contradicts. So here you can write, it implies alpha 1, alpha 2, and so on, all the alpha n minus 1 till alpha n minus 1 alpha n is equals to alpha is equals to 0, there, which contradicts that capital A is linearly dependent set. Okay, so that's why alpha cannot be 0. Therefore, alpha is non-zero. If alpha is non-zero, I can easily find out this V here, this V from this equation. So if I take this to be 2, then from 2, it implies from equation 2, I can write what would be V. V is minus alpha 1 divided by alpha V1 plus minus alpha 2 by alpha V2 plus and so on minus alpha n by alpha Vn. What does it mean? See, we have written V as a linear combination of the vectors V1, V2, Vn. These are the vectors from your S. That's why I can say it implies V belongs to linear span of S, which means capital V is a subset of L of S. That's your equation number 3. So from 1 and 3, V is equals to L of S. Therefore, S is basis of V having n elements. This was your first question for 10 marks. We have another part from the first question itself. That's your question number 1B, again for 10 marks. Let one question from the linear transformation will always be there, so you cannot skip this topic, and it is very easy. These are very easy questions. Let T is a linear transformation from R2 to R3, such that T of 1, 0 is 1, 2, 3, and T of 1, 1 is there. So you have to find the linear transformation of 2 and 4. So see, what is given to us? Given is transformation on 2 elements. 1, 0 is 1, 2, 3. 1, 2, 3. And T of 1, 1 is minus 3, 2, 8. Right? And we need to find here linear transformation on 2, 4. If linear transformation is given on the vectors that constitute basis of the vector space, then we can find linear transformation on any element. And that's what we have to apply here. Linear transformation on 1, 0 and 1, 1 is given. If I can prove that one set containing 1, 0 and 1, 1 is actually basis of your R2, then we are good to go. We can find the linear transformation on any element, and hence on 2, 4 as well. So, see, we have linear transformation T from R2 to R3, where R2 is what? R2 is xy. X belongs to real, y belongs to real. And similarly, R3 is xyz. xyz belongs to all reals. Consider set V consisting of 1, 0 and 1. So we are going to prove that this is basis. That is equals to V1, V2, set. Definition of basis I have discussed in first question as well. I'll repeat. Basis means you have to prove two things here. Number one, B is a linearly independent set. Number two, linear spanning of B is your complete vector space. So first thing is very easy to prove. You can simply write, see, whenever you have two vectors in a set and you want to prove them to be linearly independent, you just check scalar multiplication. If one is a scalar multiple of the other or not. So V1 is not scalar multiple of V2. That's it. Therefore, B is linearly independent set, right? Next part is to prove linear spanning, in which again, first part is very easy, that we have done in the last question as well. First part is very easy. See, also B is a subset of R2, which implies L of B. Linear spanning of B is a subset of R2 as well, because R2 is a subspace. R2 over R is a vector space. For the other way around, I have to take an arbitrary element of R2 and I'll prove that that is a linear combination of the vectors in a B. So let xy belongs to R2, which implies, okay, and we can write that as A times 1, 0 plus B times 1, 1. If I can find the value of this small a, small b, unique values, then that is done. We can prove, then we can say that yes, xy is a linear combination of vectors in B. So it implies x is equals to a plus b and y is equals to b. So value of b is already y and value of a would be x minus y. So we get unique values of a and b. It implies xy can be written as x minus y times 1, 0 plus y times 1. Let's say, okay, this is linearly independent. That's first. That is second. And this is going to be third. Therefore, I can say xy belongs to linear combination of B, which implies R2 is a subset of linear, sorry, not linear combination, linear span of B, linear span of B. This is 4. So from 2 and 4. From 2 and 4. So one containment was given by equation number 2, which is linear span of B is a subset of R2 and R2 is a subset of linear span of B, which means from these two equations, I can say R2 is nothing but linear span of B. And first is B is a linearly independent set. Fifth says that linear span of B is R2. That means both the 2 points for being basis of R2 has been proved from 1 and 5. B is basis of R2. Okay. Now, if it is basis of R2, then from equation 3 says T of xy. You can see here, this is 3. From 3, I am applying linear transformation on both sides. So T of xy is equals to T of x minus y times 1, 0 plus y times 1, 1. T can be distributed. That's why it's a linear transformation, right? So T of xy is what? X minus y T of 1, 0 plus y T of 1. And we know the value of T of 1, 0. T of xy is equals to x minus y. T of 1, 0 was 1, 2, 3 plus y times T of 1, 1 was minus 3, 2, and 8. Minus 3, 2, 8. So this will be x minus 4y, 2x, and 3x plus 5y. You have a general linear transformation. Now you can find out for 2, 4. That is equals to, substitute, it will be minus 14, 4, and 26. That's your answer. Next. This is a second question, the first part for 15 marks. Let's see what the question is. This was a very easy question. Find all solutions to the following system of equations by a row-reduced method. Okay. So, given row-reduced method, that means I have to reduce the matrix, coefficient matrix into the row-reduced form. Let's see how. So, what is given? Given is a system of equations. Given is AX is equals to B, where A is your coefficient matrix, 1, 2, minus 1, 2, 3, 5, minus 1, minus 3, and 8. X is the vector of unknowns, that is x1, x2, and x3. And B is 2, 5, and minus. Okay, so we'll consider an augmented matrix here. Consider augmented matrix and we'll reduce it. So let's see. 1, 2, minus 1, 2, 3, 5, minus 1, minus 3, 8, slash 2, 5, minus 1. Let's start. So let us apply on R3, operation R3 plus R1, and on R2, let's apply R2 minus 2R1. So that would be 1, 2, minus 1, 2. So this is going to be 0, minus 1, 7, 1, 0, minus 1, 7, and 1. Yeah, we can clearly see on applying R3, R3 minus R2. So last row becomes 0. This is 1, 2, minus 1, 2, 0, minus 1, 7, 1. We want to find a row reduced form. Okay, this is going to be 0 also. We want to find a row reduced form here. So let us make this also as 0, right? So in a row reduced form, what happens is, for example, this is C. This is the first non-zero row. This is the first non-zero row. In a non-zero row, what is the first non-zero entry? 1 is the first non-zero entry. In that particular column, we should not have any non-zero entry except that itself. So except that one, we don't have any non-zero entry because all of them are 0. Let's talk about the second row. Second row is also a non-zero row. What is the first non-zero value from left? That is the first non-zero value. So in this particular column, I should not have any other non-zero value. So 2 is another non-zero value. So that's why I'm trying to make that 2 as 0. So that would be, I can do on R1 plus 2 times R2. So that would be 1, 0, 13, 4. 0, minus 1, 7, 1, 0, 0, 0, 0. And the first non-zero entry in each non-zero row should be 1. So that's why let's just change second row. 0, 1, -7, -1, 0, 0, 0, 0. This is on R2, just multiply -1, which is required row reduced echelon form, which is required a row reduced echelon form. What does it mean? After reducing it into this form, we get that rank of A is actually equals to rank of augmented matrix, which is 2. But it is less than number of rows in A. What does that mean? It means the given number of linear systems are consistent, having infinitely many solutions. It implies given system of linear equations are consistent, having infinitely many solutions. Okay. Therefore, AX is equals to B is equivalent to solving, is equivalent to see, this is this matrix equivalent to 1, 0, 0, 0, 1, 0, 13, -7, 0, and okay, this will be written there, is equivalent to this x1, x2, x3 times 4 - 1, 0. 4 - 1, 0. Okay, so we have to solve this. Let's find the equations. Equations from here are x1 plus 13x2 is equals to 4 and x2 minus 7x3 is equals to -1. So it implies x1 is 4 minus 13x3 and x2 can also be, we can also get x2 in terms of x3, 7x3 minus 1. Therefore, what is the answer? Answer is x1, x2, x3 is equals to 4 minus 13x3, 7x3 minus 1, x3, where x3 belongs to real. So these are your values of x1, x2, x3, and hence solved. So this we have solved by reducing them to the row reduced echelon form. This was for your 15 marks. Next, third question had 2 parts, 10 plus 10, so total 20 marks question. Prove that P is a subspace of R3 and find the basis and dimension for P. Okay, let's see what is given. P, we can clearly see that it is a subset of R3, right? So given, let's write given. Question says, let the set P, which is given, XYZ with the 2 conditions on it, be a collection of vectors of a vector space R3. So yes, it is a subset of R3. I want to prove that it is a subspace. And after that, I have to find its basis and dimension as well. Okay. See. So given is a collection of P. Yeah. And that's it. Yes. So we can start the first part. See, what is the definition of a subspace? A subset. First of all, it has to be a non-empty subset of your vector space. If it is a non-empty subset of your vector space R3, then it is a subspace of R3 if and only if alpha x plus beta y belongs to P for all xy from P and for all alpha beta from your field R. So if that is true, I can say that P is a subspace. And that's what we are going to prove here. So let's take, let alpha beta belongs to the field, and that is R, given here, R3 over R. And let us take two elements from your P set. So let X, which is equals to X1, X1, Y1, Z1, and Y, which is X2, Y2, Z2, belongs to P. If it belongs to P, that means these two conditions should be satisfied for both of these elements. It implies X1 minus Y1 minus Z1 is equals to 0. And 2x1 minus y1 plus z1 is equals to 0. These are the two conditions, x minus y minus z and 2x minus y plus z is equals to 0. That is second. And for the another one also, x2 y minus y2 minus z2 is equals to 0. And 2x2 minus y2 plus z2 is equals to 0. Then let's try to find alpha x plus beta y. I want to prove that this also belongs to P. See, if an element of R3 belongs to P, that means I want to prove that these two conditions are satisfied. If these two conditions are satisfied, that means yes, that element belongs to P. So alpha x is equals to beta y would be alpha times x1, y1, z1 plus beta x2, y2, z2. It is alpha x1 plus beta x2, alpha y1 plus beta y2, and alpha z1 plus beta z2. In order to prove that this belongs to P, I want to prove those two relations. Where first relation was x minus y minus z. So here it will be alpha x1 plus beta x2 minus alpha y1 plus beta y2 plus, not plus, minus alpha z1 plus beta z2. Open this, alpha common, x1 minus y1 minus z1, and beta common, x2 minus y2 minus z2. These two brackets are individually 0 from equation 1 and 3. From equation 1 and 3. That's why this is equal to 0. And second was 2 times x minus y plus z. So again here also, if I take alpha common, I'll get 2x1 minus y1 plus z1 plus beta times 2x2 minus y2 plus z2. That is equals to alpha times 0 and beta times 0, because these brackets are again individually 0 from equation 2nd and 4th. This is from equation 2nd and 4th. So that is equals to 0. Therefore, I can say, therefore, alpha x plus beta y belongs to P, and it implies P is subspace of R3. Okay, first part is proved. Here you secure your 10 marks. For the next 10 marks, what I have to find? I have to find its basis and dimension. So let's get back to the definition. What was it of P? How P was defined? P was defined. Okay. So P is equals to x, y, z, where z is equals to x minus y. I have written in a slight different way. I have taken the value of z here, and 2x minus y plus z is equals to 0. So in these kind of questions, what we do is we try to eliminate variables one by one. For example, here I have value of z. So in the next step, I'll be eliminating this condition by substituting the value of z everywhere. So it would be, it can be written as x, y, and x minus y. That's the value of z. I'll not write this condition, and I'll write the condition 2x minus y, again substituting the value of z, x minus y is equals to 0. So this will be equals to x, y, x minus y, where 3x minus 2y. So what I'm going to do next is going to eliminate the next variable, y. Let's eliminate y from here. So y is going to be what? 3 by 2x. And I'm not going to write this condition anymore. So that is equals to x. What is the value of y? Y is 3 by 2x. X minus 3 by 2x. Where x belongs to the real. So this becomes x 3 by 2x and minus 1 by 2x. X belongs to real. I can take x common, and you can clearly see that this can be written as, so P is x common, this is 1, 3 by 2 and minus 1 by 2. X belongs to real. So can I say that it is a linear combination of a set containing this vector? I can clearly say from here that P is a linear combination of a set containing only this vector, 1, 3 by 2 and minus 1. And since it is a non-zero vector, that means this set is a linearly independent set also. So that's the basis. Therefore, basis of P is what? Set containing 1, 3 by 2, minus 1 by 2. Because this is a linearly independent set. It's non-zero. Because set containing 1, 3 by 2, minus 1 by 2 is non-zero. And hence I can say dimension of P is 1. So here is your basis and dimension is 1. And here you secured your another 10 marks. Last question was very interestingly, yes, this was for 15 marks. Question number 4A, find a linear map T from R2 to R2, which rotate each vector of R2 by an angle theta. Also prove that for theta is equals to pi by 2, T has no eigenvalues in real numbers. Okay. So if you can make an intuitive picture of this question, it would be very interesting to solve actually. Let's see. Let's say this is my y-axis and x-axis. What does the question say? Question says, you want to find a linear map from R2 to R2, which rotate each vector of R2 by an angle theta. So see, I want to find this question you can actually associate from the question that we have done here in, like, yes, second question, actually, first B. What was the question here? Question was to find a linear transformation of a vector, given that on two vectors it works like this. So how can you find linear transformation on 2, 4? But the point was here in this question that these two vectors on which linear transformation is already known, those two vectors must constitute your basis of your vector space, domain vector space, R2. A same kind of scenario is happening here. I want to find a general linear transformation, but if somehow I can find out that how the linear transformation work on a basis vectors, then I can find a general linear transformation also. So let's try to find out the transformation, how that works on just two elements. Those two elements will be basis vector. Okay, and we'll prove that also, that it's a basis vector. Let us take standard basis, E1, E2, 1, 0, and 0, 1. So I'll talk about each of them separately. First, let's talk about 1, 0. Okay, so in 1, 0, if I rotate it, that's what it says, which rotate each vector of R2 by an angle theta. So if I rotate this by angle theta, what would happen? Let's say this is the point P. And after rotating with angle theta, let's say it is here at P. So this was original position. And after rotating this vector by theta, this is the new position. So let us take this to be, okay, what is the distance from 0 to that point, from origin to that point? That is 1, right? Because it is 1, 0. So it is 1 cos theta and 1 sin theta. Cos theta and sin theta. Right? Because this distance is 1. And this is how you have taken the position in this direction. This is what has happened to the first point. So what we have done here, I can say we know that I'm talking about two particular vectors here. We know that if 1, 0 and 0 and 0, 1 is rotated by an angle theta, then we get cos theta comma sin theta. And what about the other? Next, we would have 0, 1. Let's say this is Q, which is 0, 1. So after rotating with an angle theta, in again this counterclockwise direction, maybe somewhat here. Right? So this is also 1. And this time this is theta. So this new position of Q, let us say Q dash. Let us say this as P dash. Okay. So what is the coordinate of Q dash? Q dash, which is a new position of Q. This is a simple, this is 90 degree. Now, so you can apply sine theta, cos theta here simply, right? So see, if I apply sine theta here, it will be sine theta is equals to the distance, this distance. This distance will be 1 sine theta. 1 sine theta. But this distance is 1 sine theta, right? Not the abscissa. Abscissa, it will be negative because we are in the negative direction of x-axis. So abscissa would be minus sine theta, and cos theta will remain as cos theta. So this is cos theta. So this is minus sine theta, cos theta, respectively. And if I know linear transformation on two vectors that constitute bases, that means we are good to go. We can find the general linear transformation as well. Okay. So consider B is equals to 1, 0, 0, 1. These are standard bases. We will prove that these are bases of R2 so that we can find the general linear transformation. That is equals to V1, V2, say, Again, to prove they are linearly independent, what we can do? Since V1 is not scalar multiple of V2, I cannot multiply any real number in the first vector to get the second vector. So it's not linear scalar multiple of V2. Therefore, B is linearly independent set. For the second also, it's very easy. Also, linear spanning of B is V. I can clearly write that. Why? Because see, because clearly linear spanning of V is a subset of V, and XY is X times 1, 0 plus Y times 0, 1, which implies V is a subset of L of V. So it's linear independent also, and these two containments are also true. That's why that's a linear span of B also. Therefore, I can write B is basis of capital B. Right? Now, we can find linear transformation. We know xy is equals to x times 1, 0 plus y times 0, 1. Let's apply linear transformation on both sides. T of xy is equals to x of t of 1, 0 plus y t of 0, 1. We know linear transformation on these two vectors. T of xy is equals to x cos theta comma sin theta plus y minus sin theta comma cos theta. So T of xy is going to be x cos theta minus y sin theta comma x sin theta plus y cos theta. Also, this T of xy can be easily written as cos theta minus sin theta cos theta xy. What will be this matrix for theta is equals to pi by 2, right? That's the second part. Also prove that for theta pi by 2, t has no eigenvalues. So the matrix representation of t here, it would be this. You can multiply cos theta x minus sin theta y, that's the first component, and cos theta x plus y sin theta, sin theta x plus y cos theta, that is your second component. Now, that is cos theta. For theta is equals to pi by 2, your t would be 0, minus 1, 1, and 0. In order to find eigenvalues, we'll find characteristic equation. Characteristic equation of t is determinant of t minus lambda I is equals to 0. So that would be minus lambda minus 1, 1, lambda, minus lambda, determinant 0. This is a second order determinant. So that would be lambda square plus 1 is equals to 0. Lambda square is minus 1, and lambda is equals to plus minus I. It implies t has no eigenvalues in reals. So this is the second part that you have proved here. And first part was to find this linear transformation, and this is your linear transformation. Okay. So these were all the questions that appeared in the last year. I hope this was valuable for you. This video helped you. And with this, we'll meet in the next video. Thank you so much, everyone.